Hi everyone, my name is Chong Hao. I'm gonna host the free branch this year about driving. Basically cover some aspect that industrial side, maybe interesting, which is autonomous driving. This requires models to reconstruct or predict the high definition map from onboard sensor. This is very important in the industrial side because, as you know, many in the driving system today they rely on a very good HD map to navigate the vehicles. And then we will have another track called driving virtual language. This is more of a research-oriented track, so people might wonder, okay, now we have very good visual language model. What if we put that into autonomous driving scenarios and could it drive relatively good compared to human driver? Is it possible or not? Yeah, this track is to do a research-oriented for this purpose. And then finally, we have the color challenge. The color challenge is for now it is the only one closed loop simulator that people can do closed loop evaluation of their models. This is very different to the current well-known open loop one. Okay, the open loop one might not give a very a concrete or solid ideas of how well your model perform in many corner case scenarios. But while Kala, this year they put a Kala version leaderboard 2. This has many corner cases scenarios. Hope later the organizer will introduce it more. Okay, so let's welcome the organizer from Mapless Driving, Hui Jie. He will introduce what about the Mapless Driving law. Thank you.
I will just take it short. And in this chart, we most focus on the data element in the driving scenario. And at the very beginning of this data element, people usually focus on the 2D lane. Now the original method is to detect the lane line in the perspective view and then use the IPM to project them into the 3D space. But due to the assumption of the background assumption, the error is unreliable. So in 2022, we come up with the first real-world large-scale dataset on 3D lane detection. We make some 3D annotation in the 3D space based on the rainbow dataset, and many people from the industry have already using this data. But at the same time, we noticed that we might miss some elements on the road, like the road side or the lane topology. So next year in 2023, we come up with the second edition of the OpenLane dataset, the OpenLane V2 dataset. In this dataset, we mostly focus on the topology relationship between the lane center line and also between the lane center line and the traffic element. In this dataset, we use lane center line instead of the lane line because we think that lane center line is a more proper representation than the lane line. For example, if we have two labeling lane, the lane line in the middle is shared by these two lanes, and then we cannot attach some semantics information to it. And okay, so in the last year's challenge, we also we already have a challenge on the OpenLane V2, the OpenLane topology challenge. In this track, many participants from the industry have already participated in it. And after the challenge, they give us some feedback that the lane line is still very important for the industry users. So in the late last year, we make some update on the OpenLane V2 dataset. We include the lane line in the dataset. The way we do this is to bound some lane line to one single center line. So maybe one center line will have two lane lines on the side. And also we have add some more annotation on the pedestrian crossing and the driver area to make this annotation more close to the HD map. And also we add some SD map to the dataset so that people can use this estimate as input to their model to see if the estimate can interview the model performance of it. So in this year's challenge, we use the OpenLane V2 update as our topic, and then we also update our matrix that we calculate the average sum, weighted sum of the lane segment detection score, and then the area detection score, the traffic element score, and also the topology score inherit from the OpenLane V2. So as for the result, This track is the second most popular track in the challenger. That is surprisingly because we do not anticipate it. I think most of the participants think it is from the industry side. And as for the challenge, the team from the Longer Technology has won the challenger. This is a company in Hangzhou which is focused on HD map. So, and unfortunately, they can make it to America, and then they prepare a video on their winning solution. So, let's have it.
This is the overall model. A traffic elements detector, YALO, a lane topology, LLT, and a lane T topology, LTT. For the lane topology, we use the topo MLP method. Firstly, we pass the centerline coordinates to MLP and add them to the refined query features. Finally, we apply MLP to perform topology classification. For the lane traffic topology, we use the coordinates of centerlines and coordinates categories from traffic element bounding boxes. We train topology model using ground truth data of lane segments and traffic elements, since the feature embedding are not used. By decoupling with the upstream detection model, the training and prediction process of topology becomes more convenient. Due to the complexity of intersections, we use self-attention to facilitate information exchange among elements and obtain relative relationships. There are mainly two types of view transformation: forward projection and backward projection. Lift splat shoot, LSS, takes advantage of the depth distribution to model the uncertainty of each pixel's depth. But the drawbacks of forward projection is discrete and sparse BEV representation. BEV former projects 3D points back onto 2D images. As a backward projection, one limitation of BEV former is false correlation between 3D and 2D space due to occlusion. To address these issues, we introduce a symmetric view transformation. The depth map of each camera is generated from synchronized LiDAR point cloud. The LSS utilizes depth supervision only at the training phase. Given the SD map of the scene, we evenly sample along each of the polylanes for a fixed number of points. With sinusoidal embedding, BEV former apply cross-attention between the SD map feature representation with features from vision inputs on each encoder layer. In order to fuse BEV representations, we use the channel attention-based fusion module. Here are stacking strategy and streaming strategy, which are same as stream map net summary. The streaming strategy facilitates longer temporal association, as the propagated hidden states encode all historical information, but a temporal fuser such as CON-GRU may still face the problem of forgetting. The stacking strategy may integrate features from specific previous frames, offering flexibility in fusion of long-range information. The computational cost is linearly related to the number of fused frames. We propose a novel hierarchical temporal fusion, HTF. The hierarchical temporal fusion fully leverages local fusion capability of streaming strategy and long-range fusion capability of stacking strategy, and it minimizes memory and latency costs compared to the stacking strategy. Here we present two variants of HTF: streaming strategy and streaming stacking strategy, as shown in figure. For streaming stacking strategy, we random select in frames from the latest and previous frames for the stacking mode layer during the training phase, and select n frames by a certain distance strides during testing phase. In order to demonstrate the effectiveness of long-range stacking for streaming stacking strategy in figure, the stacking previous frame interval parameter is set to 2. Stacking strategy only fuses one previous frame in this figure, and actually it may fuse more than one frame. As shown in table, streaming strategy and streaming stacking strategy are adept at both short range and long range without linear computational cost. Inspired by MASH map, we simplified the PET crossing by 4 corners. Then we unified the 4 corners into the map-TR form of endpoints. The main difference is that map-TR uses 20 evenly sampled points, MASH map uses 4 points, and we use 6 points evenly sampled on each edge, as shown in figure. Our pet crossing representation keeps for corners as key points, which are essential shape priors. What's more, the permutations of pet crossing are simpler than MapTR. Compared to MapTR's 40 equivalent permutations of 120 points polygon, LG map only requires 8. Instead of point-wise permutations, we only use corner-wise permutations. Lastly, preserving corners is beneficial for instance query embedding. We examine the efficacy of SVT component through ablation studies, utilizing the OpenLaneV2 dataset. Starting with BEV-Former and LSS as baseline, the best score is 40.36% on the validation set, as shown in table. Compared to the best baseline, the integration of BEV-Former and LSS increased 0.5% MAP after adding image data augmentation and BEV data augmentation. The model performance has improved to 43.75%. We build a single-frame baseline model by training 72 epochs with raised net 50 checkpoints, and then all experiments fine-tune the baseline model by 12 epochs. We use single-frame mode to fine-tune the baseline model. Model can reach a score of 52.93% MAP, as shown in Table 2. For the streaming strategy, we use one conv-GRU as dense fusion encoder. It has a performance improvement of 3.7%. And for the streaming strategy, 2 layers of conv-GRU are used instead of 1. Unfortunately, the performance increase only 0.56% compared to single frame. For the streaming stacking mode, we select for frames out of latest 10 frames for the layer of stacking mode during training phase, and a certain distance strides of 5, 10, 15, 20 meters during testing phase. The performance reaches 57.13% MAP. We use the hierarchical attention-based decoder same as MapTR as baseline. The model performance reaches score of 33.6% DETA, as shown in table. Then we change the decoder to instance attention. The model performance increased 0.45%. Finally, we utilize pet crossing resampling to improve the performance to 35.42%. YALO V8 with data augmentation can reach a score of 79.42% on DETL, as shown in table. Applying resampling has a performance improvement of 0.64%. TTA further improves 1% score. We utilize pseudo label to improve the performance to 81.81%. Finally, the model ensemble of YALO V8 and YALO V9 improve the performance to 82.4%. We train 3 versions of models using different backbones, VIT, InterImage XL, with different input image resolution scales, 0.5, 0.75, 1. During the ensemble process, we utilize an ensemble strategy that incorporating predictions with low similarity. Initially, the models are sorted by their evaluation scores. The best model is the base model, and the other 2 models are subsequently integrated as proposal models. From the table, it can be seen that the more models ensemble, the more remarkable performance improved. In this work, we rethink the pipeline of 2D, 3D elements detection and topology reasoning of mapeless driving. Firstly, we employ a symmetric view transformation, SVT, to combine forward projection and backward projection to form complementary advantages. Secondly, we introduce the hierarchical temporal fusion, HTF, to integrate temporal features from local to global stably. Moreover, we improve pet crossing representation by a novel resampling method. Finally, LG Map is the first place solution on the mapeless driving track, which achieves 0.66 Uniscore.
Okay, thanks for their thanks for their talk on their methods. I won't say there are many of the tricks listed here are novel or so, but these tricks are really useful when you want to improve your model and you get better score. This is very useful in this stage.
In this video, we introduce.
Okay, then so here I'm going to introduce about driving with language tracks. So this is more research-oriented one. Okay, let's start it. So we start with a very simple concept about end-to-end driving with language. So first of all, so what is end-to-end driving? So people now think that there are 3 components that is really important in the end-to-end driving system, which is the perception, prediction, and planning. Perception requires the model to answer what are the wrong, basically object detection of the surrounding environment. Then when it goes to the prediction stage, it will tell us how will the other vehicle or other pedestrian go in the future. So it's more like a future prediction task. Then based on these two tasks, we will tackle the final task, which is planning. It is more of the ego vehicle planning. Then where should I go? Now this is a very simple concept in the end-to-end driving, but we have an answer on this. Like if we have a visual question answer data for each stage, how can a vision language model drive under this context and have better performance or on-par performance compared to previously conventional driving systems? So why, before asking how to do it, let me ask, why do we want to do that? Because intuitively, vision language model, they are pre-trained on an internet scale data, having more explainability and generalization. These are the motivation, but I think this motivation is really important, but more important is how can we make this happen? So then we have a human label data set on all the visual VQA data in the driving scenario. This is an example of what the data looks like. So it basically interpret the idea of perception, prediction, and planning with some human label question and answer in these scenarios. And we have a very strict data labeling pipeline to ensure that each scenarios and each vision QA pairs are following the main idea of the driving of the human driver. Then it follows the human driver to some extent. And we both work on this both on the NewSense and Carla, which are two prevalent data sets in the driving community. And actually, the driving with language task didn't come from nowhere. Actually, from when we date back into 2018 or 2019, there are some data sets working on it. But as you know, after ChatGPT released their work, there were so many works working on this, and people are buying that, okay, we put vision language model in it, and we will have some potential to do better reasoning or better logical thinking in the driving scenarios. And there's some stats about this. Seems like this track is the most attractive one in the worldwide this year. So we have 152 teams ranging from academia to industrial, and we have a total nearly 1,000 submissions. And interest that didn't come from academic only. There's many industrial friends also interested in this track as well. So like NVIDIA, AMD, Tencent, and so on. And here's the leaderboard. You can see on the website. And this is the most important part, I think, about this challenge. It actually tells us about two insights about what will be the future of driving with language. The first one is how to align humans' preference and the VLMs pick up on the important objects. We see that there's a super misalignment on these two things that we actually ask the human driver to annotate many important objects in the scenarios, but vision language model usually has a different understanding on that. So how to align these two things is very important if we want to really adapt the vision language model in a driving system. So some possible way to do this might be we could strong alignment or test time adaptation, which is very prevailing these days. And the second thing is that, okay, how do we explore the visual reasoning with the current vision language model? So as you know that for now, vision language model doesn't have a really in-context learning. The in-context learning part ideally comes from the language model itself, but it didn't have to interview with the vision part. So how to do that in the driving system? First of all, this is very important because you need to do the reasoning between the perception, prediction, and planning part. But how to do that, we still see a very clear roadmap to this. And also about some limitation of the current work, like the vision language model couldn't handle complex sensor configure like LiDAR, MIU, and so on. And also we will want to do this in a closed loop manner to get more solid conclusion. And then the final reason about final point of the vision language model is the runtime friendly. And let's welcome the first place of the driving with language track from Nanjing University. Here, Zhixi will give us a talk about how their methods reached the first place. Let's welcome.
Okay, hello, I'm Zhiqi. Today I will introduce our champion solution. I'm on behalf of Jiaha and Tonglu. Firstly, I will briefly introduce the dataset DriveLM. You can see that DriveLM is a typically weekly type task, and it evaluates the model's capability in perception, planning, and prediction for driving scenarios. There are 4 types of quotients on this data set. We can see that different type of quotient, they have different evaluation metrics. It's worth noting that DriveLM represents the object with its center point. Actually, we are not satisfied with this representation for the following 2 reasons. Firstly, the point representation is not more accurate than bounding box representation. And the second reason is that existing VLMs like Lava or InterVL, they use the bounding box representation. If we want to inherit their perception capability, so we better to use bounding box representation rather than the point representation. So in this solution, we employ a simple strategy with the segment anything. We use a point as a point form to get the corresponding masks and then the bounding box. This works well for the most cases, but it may fail in some cases like traffic site. For our base model, we use InternVL. InternVL consists of LM, InternLM V2 20 billion, and the vision encoder InternVIT 6 billion. And the connector is MLP. To support high resolution image input, InternVL employs image division strategy. It splits the high resolution image into the many smaller image. So we can see the performance of InternVL in the commonly used benchmarks. InternVL rank first in typically used benchmarks such as MMB or MassWestern. So we can see that InternVL is one of the most powerful open source VLM, and we choose this base model. For this DriveLM dataset, there are several adaptations. Firstly, nuisance has multiple views, but InternVL only support training with one image. So we simply combine these different views into one image, and we also add corresponding text on this image. We also should resize this image to 448 times 896 so that one view will be split into 2 sub-images, so while no information broken. So with this simple strategy, we can fine-tune InternVL on this DriveLM dataset. We also indicate the layout in our system prompt. We tell this InternVL model it will be autonomous driving task specific. For our training setting, we use a 4-parameter fine-tuning strategy and train the model with 1 epoch, and the visual token is around 3,000. We also use a deep seed 0.03 strategy. So after that, we can directly obtain a very impressive performance. For V1, we only use 10% of data. For V2, we use the full training data. We can see that with V2, we achieve a score of 0.6, which ranks first. We found an interesting thing is that in this challenge, it used GPT as a referee to evaluate the similarity between the predicted natural language and the GT language. This is their code. It's very simple to understand. So we found an interesting thing is that if our predict answer is, we can play GPT by changing our predict answer. Like if my answer if I set my answer to be, my answer is same with GT. Both GPT 3.5, GPT-4, it will directly give me 100 score. For GPT-4, it's a little bit smarter. It may give a score like 0, 41, or 28. So I think this using GPT as a referee maybe should be reconsidered in the following competition. So that's all. Thank you.
Thanks for Zhiqi's talk. Then we have a second place talk from Team Media presented by Zhiding. So he will introduce what their method is about. Wait a second. Okay, let's welcome Zhiding from NVIDIA to introduce driving with multimodal large language model.
Okay, thanks for the introduction and apologize for my broken voice due to the cold. So yeah, I'm from NVIDIA. My name is Zhiding, and we are presenting the second place solution of the driving with language challenge. Yeah, so here's a brief overview of the challenge. So in this challenge, there are mainly four types of questions. So important objects, for example, decision making, motion prediction, and grounding. So the reason why we are interested in participating in this challenge, besides what Chonghao has mentioned, internally we found that we could use language models for a lot of very interesting applications for AV. For example, we can do offline data auto labeling. We could also do high-level decision making as an auxiliary information for the planner. We could explain our planning decision as a confidence view. And finally, we could also do like planning-oriented data curation and retrieval. So these are only a few applications, and there are many more. So I want to briefly introduce two works from NVIDIA on multimodal LM, and our challenge is pretty much, our challenge solution is pretty much built on top of these two works. One is called Eagle. It is a 2D multimodal LM with state-of-the-art performance. The second one is OmniDrive. It's actually a multimodal LM that is able to take multi-view camera input, and is a 3D multimodal LM. So in this case, it's pretty much hello. Okay. Thanks. Okay. So yeah. So multimodal is a 3D multimodal LM. So I want to show some also very interesting cases. I feel these cases are very difficult to be addressed by regular rules. If you write if-else, if you try to write a lot of these cases, there will be many of these in the wild cases that it would take you forever to write rules. So in these cases, LLMs are very good toolkits to handle these cases. For example, choosing which lane to take. And on the right is also a lane merging example. Sometimes your cars need to make these high-level decisions, and the model our Eagle model is able to make a pretty decent reasoning by looking at the traffic signs and also recognizing there is a left merging sign on the lane and tell you, okay, you should be prepared to merge to the left lane. There are also some more hard cases. For example, when you have a plane on the road, which you have never seen, or you are in a parking lot where it's highly unstructured and it's not like a regular urban driving scenario. We also show an example of OmniDrive where you can drive, you can give the reasoning, joint planning and reasoning, while at the same time reason why are you making such a decision. So this is one example where it sees the pedestrian and it's able to say, okay, I need to stop. This is another example that it's following the car, and it knows okay, it's you should not overtake the front pickup the truck, delivery truck, because it's dangerous. Okay, so our challenge solution is built on top of these two works, but with some modifications. So we found we will share some of these tricks, and we found them useful. So as you can see in this figure, so we incorporated temporal information by reading multiple frames. We also incorporated ego pose as pose token to the language model. And finally, we also leverage detection models, 2D detectors as specialist models, and we can input their detection results as tokens, also as part of the tokens into the language model. So overall, here's how we started from the baseline with a 53 score, and we added temporal information. This will bring our score to about 54, and then ego pose, and then we use Llama 3 AP. We actually didn't use a very huge language model here. If we use a bigger language model, for example, E34B, possibly we could get a higher GPT score. Use a 2D SFT web data from the that's the SFT data used by the Ego project. And also we found that a lot of the driving scenarios are very simple, straightforward driving. So if we try to balance the data better and try to read more about the corner or difficult cases, it will improve accuracy greatly. Finally, we add a 2D object detector, and it can further boost the performance a lot. Okay, so I think that's all for the presentation. Thank you.
Okay, thanks for Jading's work. So next we will, since the Kara group couldn't come to our event, so they prepare a video as well to introduce the Kara challenge.
Hello, my name is Matt. I'm the technical writer for the Carla Simulator development team. And I'm delighted to welcome you all to the workshop for the Carla Autonomous Driving Challenge 2024, hosted as part of the Autonomous Grand Challenge at CVPR 2024. We're very grateful for the excellent participation in the challenge and your attendance of the workshop as well. We'd like to express our appreciation as well to our sponsors for their ongoing support of the leaderboard challenges, which enables us to host one or more challenges every single year. This challenge has been made possible by the dedicated work of our organizers from within the Carla team itself, as well as Eval AI and our partners and sponsors, Synchrotron. So let's start off with a short introduction to the leaderboard. The aim is to provide an open testbed for evaluating the driving proficiency of autonomous driving agents by challenging them with a common series of routes, driving scenarios, and traffic situations. Each agent's behavior when confronting these challenges is then captured by a series of metrics quantifying driving proficiency in a consistent and repeatable way. Thus, we aim to accelerate progress in the research community through collaboration and competition within the leaderboard. And for this reason, we ensure free access to researchers, engineers, and enthusiasts through an open source distribution model for Carla and the leaderboard itself. The leaderboard works in the following way. AD systems are presented with a set of routes that they have to navigate under varied weather conditions while properly addressing a number of complex traffic situations, like, for example, merging into traffic, moving around obstacles, or emergency braking. We synthesize as many of these traffic situations as possible into a set of short routes. You could think about these routes as being like the most challenging day in your life as a driver. The leaderboard has two challenge modalities, or tracks as we call them. The first is the sensors track, which provides data from a standard simulated AD sensor suite with up to 8 cameras, 2 LiDARs, radar, GNSS, acceleration data, and speed. The second map track also provides privileged information about the road network from the OpenDrive map, placing more emphasis on planning and reducing perception complexity. Once the agent has completed all the routes, the leaderboard then uses a set of metrics to quantify driving proficiency. This includes assigning scores and penalties for the amount of each route completed, infractions such as collisions with other vehicles, pedestrians, the environment, or traffic signal infractions. Driving over cautiously, agents are expected to maintain a minimum speed, and scenarios also have time limits. Agents are also expected to deal with evolving traffic situations, for example, yielding to an emergency vehicle when one approaches. These scores and penalties are then combined into an overall driving score, which is representative of the driving proficiency of the agent. Now let's move on to talk about this year's CALA Autonomous Driving Challenge. We've had excellent participation with over 20 teams approved for the competition, around 280 total submissions, and more than 50,000 virtual kilometers driven by autonomous agents. So it gives me great pleasure to announce the results of the challenge. There were many excellent entries from around the world, with scores far exceeding those of previous years of the competition. The top scores in both tracks were taken by two teams, with LLM4AD taking the first place in the census track with an impressive score of 6.87, while Tübingen took second place. Tübingen AI then took first place in the map track with an impressive score of 5.56, while LLM4AD came in a close second. Therefore, the honorable runner-up prize is awarded to Tübingen AI for taking first place in the map track and also second place in the census track. So congratulations to Tübingen AI for their impressive performance. And finally, to the overall winner, the Outstanding Champion Award is awarded to LLM4AD for taking first place in the census track with an impressive score of 6.87, while also ranking second in the map track. And additionally, the LLM4AD team is awarded the Innovation Award for their innovation of using a combination of large language models in their autonomous driving solution. And I'll finish with another thank you to everyone for participating in the competition. Many congratulations to all the teams that competed and especially to the winners. Next, we'll enjoy a presentation from the winning team, LLM4AD, about their impressive solution. Thank you to everyone for attending, and we hope that you enjoy the workshop.
Thanks for their introduction. So let's welcome LLM4AD for their talks on
Hello.
the. Oh, sorry. Okay, here we go.
Yeah, hello. So my name is Katrin. I'm doing a PhD at University of Tübingen, and this work is part of my current internship at WAVE. So yeah, I'm gonna present our winning solution to the CALA challenge, which is CALAVA, Vision Language Model for Camera-Only Closed-Loop Driving. So we heard also in the previous challenge a lot about like language models for driving. So I think there's like quite some hype and interest around that. But I still want to go a bit into like, why do we want to do it? Why do we want to use language models for driving? Why do we want to combine those fields? I think there are quite some open problems still in autonomous driving. And one big thing is like generalization to unseen objects. We have weird things maybe on the street. And we still want to be able to handle those objects. But not only objects, also weird situations like an earthquake, a flooding. I don't know, it's not happening very often, but we still want to be able and make sure that our vehicle is handling those situations and not like randomly crashing into things. Then reasoning, a big thing. So maybe some of you have seen this example of like a man wearing a t-shirt with a stop sign on it. And then there was an autonomous vehicle stopping for this man standing there. So we don't want to have this happening. So the model needs some kind of reasoning ability to reason about, oh, this is a vehicle, a person wearing a shirt and not like a proper stop sign. Then there's like this whole explainability topic. And we still care about performance. So we don't want to have like explainability. We don't want to have the model outputting language, but therefore getting a decreased performance. So we do care about driving performance in the end. And that's also why we try to make a model for the color challenge, which we can test closed loop, which gets a good performance in the end. And then we can use this model to do research and to do more work into the direction of like generalization, reasoning, explainability, and so on. So our entry is basically the basis for everything, everything else. So what did we do? As I mentioned, we have like a VLM baseline for driving on the Color Leaderboard 2.0. And as the organizers already introduced us, I think I don't need to go into too much detail here. So I directly go to our architecture. Our model is based on like roughly the architecture of a VLM, like the Lava VLM, which is like the vision encoder is based on the CLIP VIT. And the problem with like a CLIP VIT is the largest trained model has a resolution of 336 times 336. But we need, like for driving, we need a higher resolution. And that's what also Lava proposes is, okay, we just split our image into multiple patches, and then we encode those patches independently. We concatenate the feature maps afterwards, and then we have, again, like the feature map of the whole image. So this is basically what we are doing. So we have here our front view image. We split it into 2 parts, and then we encode it. And here also, an additional note, we only use images. We don't use LiDAR or any other modality. So then we have this vision features, and then we have a Llama architecture in our case, which does like the planning part. So we linear project the vision features, and then in addition, like in the middle top, we also encode like our target point so that we know on an intersection, for example, if you want to go left or right, also the ego speed. And then as our output representation, we have the path and we have waypoint. So basically for each waypoint for the path, we give like an input query, and then we encode this waypoints, and have like a loss on that. So we split basically the representation into path and waypoint. So path is space condition. So every meter we have a waypoint, and we use that for lateral control. And then we have the time condition waypoint. So it's like every 0.2 seconds is one waypoint, and we use that for longitudinal control. Then because we use like the architecture of VLM, what we can do is we can just add language to our language model. So in this case, we just like after we predict our waypoints for driving, we just add like language tokens, which is basically commentary. So it just comments on what the model is currently doing. But that's not all. Like, I think the architecture is a big part, but to get like state-of-the-art performance on Carla, there are also a lot of other steps you need to have a look at, and which are quite important. So I also want to quickly talk about those. So first of all, because it's just a simulator and not like a data set you just get and you can use, you somehow need to collect data. So you need someone driving through the simulator to collect data. And because I don't want to sit there for hours and hours and drive through the simulator, we basically need an algorithm, like an expert algorithm, to drive through the simulator. So we used PDM Lite here. It's part of another project, and it's basically a rule-based privileged expert specifically designed for the Color Leaderboard 2.0, which can basically solve all these scenarios and all these like edge cases and so on. Then with this expert, we collect a data set in like different towns, different weathers from all these different scenarios. And in total, we collect like 2.9 million samples. For training, we split those samples into different data buckets. So one bucket could be, okay, I stop for a red light. Another bucket could be, okay, I need to heavily steer into one or the other directions and so on. So basically all the buckets contain like some kind of interesting data that we don't need to train too much on like just driving straight, because to be honest, like most of driving is quite boring. So it's just driving straight, not much is happening. So we want to make sure that we train on the interesting data. Then, of course, one big thing is like the pre-training of our model. So we use this clip VIT. So we have some kind of like internet scale vision language pre-training. And here I also have some results. So our model in the end got like the 6.87 driving score on the leaderboard. If we remove the pre-training stage, so we train completely from scratch, we get 0.45 driving score. So here we see how important this pre-training step is. And then we also have an ablation on using a ResNet34 pre-trained on ImageNet, which was like commonly used on the old leaderboard from most of the state-of-the-art models, which also got like only 2.7 driving score. Then another thing is the metric. So there is some like caveat in the metric that because the routes are so long, so the routes are 10 kilometers long. And for models that are like, I think below 96% solving each scenario, it's better to not solve the long route, basically the whole route, and to stop a bit earlier. So this is something super specific for the Collar challenge and for this metric, but it cared in the end for the end solution. So I thought I still want to talk like very shortly about it. So here we have like the driven meters, so 1.3 kilometers and so on, and you see how this matters for the end score. So this was also something quite important to have a look at in the end for the end score. And then last thing I want to mention, there's also quite some variance on these long routes. So there was also a tiny bit of luck involved to get like a good run. Yeah, but results. I think we saw already the leaderboard. So we got on the sensor track this 6.87, which got us the first place here. But I also want to show some qualitative examples. So this is the model I just presented, which also generates the language. So we have here, for example, this the scenario where we have a construction site in front of us, and then there is oncoming traffic on the other lane. So we basically need to wait for a gap in the traffic and then swerve around this construction site. And our model here says, okay, the ego vehicle is waiting for a gap in the traffic before changing lanes to the lane with oncoming traffic to go around the construction site, which is in this case correct because there is this vehicle coming. And I also have it as a video. It might be a bit fast. That's why I showed first the image. Yeah, so we want to go around the construction site. We're waiting for the gap. And then when the gap is large enough, it says the gap is large enough, so we can basically change lanes. Yeah. And this also works for like pedestrians and so on. So yeah, if you want to have a look, yeah, first, also like thanks for the whole team who was involved in this work. And yeah, if you want to see more qualitative examples, we have like a video on YouTube, so you can just have a look there. And also for more like technical details, you can have a look at the tech report. So yeah, thanks for